All right, let's dive right into this explainer. Today, we're taking some pretty dense academic source material and turning it into a real, practical, step-by-step technical tutorial on microcontroller hardware and communication. If you've ever popped open a device and wondered how all those little black chips actually talk to each other to get things done, well, you're exactly in the right place. We're going to break down the actual hardware and protocols that run professional embedded systems.
To make sure we don't get overwhelmed, here is our blueprint for today. We'll start by meeting the PIC16F887A, then decode its pin diagram. After that, we'll ask, what is SPI? Look at how SPI communicates, weigh its pros and cons, and finally, actually build an SPI circuit.
Section 1. Meet the PIC16F887A. We're starting our journey right at the physical hardware layer with the microcontroller itself. So, meet our brain, the PIC16F887A. This is a wildly popular, super powerful 40-pin chip that's just everywhere in electronic engineering. And what makes it so incredibly useful is that it's packed with flash memory. That means you can write and rewrite your code onto it tons of times. Plus, it's got this highly convenient internal oscillator. That's a huge deal because it physically shrinks your circuit footprint by cutting out the need for external timing components. Add in the built-in modules for everything from analog to digital conversion to complex communication, and you literally have a total powerhouse crammed into this tiny black rectangle. Okay, Section 2, decoding the pin diagram. Now, staring down a 40-pin chip can feel, well, a bit daunting.
I mean, let's be real, it kind of looks like a mechanical centipede. So let's filter out the noise. Looking at this map, what's really fascinating is that out of those 40 pins, a massive 33 of them can act as standard input and output pins, or I/O pins, to control external devices. They're grouped up into ports, port A, port B, port C, and so on. But they aren't just simple on and off switches. Almost every single pin here pulls double duty, serving multiple functions depending on exactly how you program the chip.
So instead of trying to memorize all 40, which, let's face it, is a headache, let's just focus on the essentials for today's build. Pin 1 is our MCLR reset. It needs a constant 5 volts, and the second it drops to 0, boom, the whole chip resets. Pins 11 and 32 provide that vital 5-volt power to the chip itself. And crucially, we have port C. Pins 18, 23, and 24 on port C are specially reserved for our SPI communication protocol. Pin 18 acts as the clock, 23 takes data in, and 24 pushes data out. But listen, a brain sitting all by itself isn't actually very useful, right? Which brings us to the core dilemma we're tackling in this explainer. How exactly do we use those specific port C pins to share complex, high-speed data with other chips without turning our board into an absolute rat's nest of wiring?
Which leads us to Section 3. What is SPI? To fix our wiring dilemma, we need to shift from physical hardware to communication rules.
We need a shared language, and that language is SPI, or Serial Peripheral Interface. Basically, it's our high-speed, synchronous solution that lets multiple chips in a system reliably sync up and talk. Now, synchronous is the absolute key word here. It means every device on the line is marching to the exact same drumbeat, which allows data to just fly back and forth incredibly fast.
Moving on to Section 4, how SPI communicates. Let's actually look at how this language structures a conversation.
The best way to think about this master and slave dynamic is like a really well-organized classroom. The master chip is the teacher. It generates the heartbeat of the class. The slave chips, they're the students, and they only speak when they are directly called upon. The master is in total, absolute control of both the pacing and the direction of the data.
So, keeping with that analogy, the teacher uses 4 specific lines to manage the room. SCK sets the rhythm, that's our clock. MOSI, which stands for master out slave in, is how the master sends instructions to the student. MISO, or master in slave out, receives the student's answer. And finally, SS, or CS, the slave select line, is used to basically tap one specific student on the shoulder so nobody talks over each other. If the master wants to chat with a specific slave, it just pulls that slave select line low. Simple as that. All right, Section 5, SPI pros and cons. Because as with literally any engineering decision, choosing SPI involves some trade-offs.
Right, so it's not a magical fix for every single circuit. The big takeaway here is that while SPI gives us incredibly fast, full duplex communication, meaning data travels in both directions at the exact same time at speeds up to tens of megabits per second, it definitely comes at a cost. It requires a lot of wiring. Since you need a dedicated slave select wire for every single new device you add, your circuit can get super crowded super fast. On top of that, because it's so high speed, you've got to keep your cable lengths really short to avoid signal noise.
Now for Section 6, building the SPI circuit. This is the payoff, folks. Let's take all this theory and actually wire it up.
But before we touch the hardware, we have to write the logic. This flowchart brilliantly maps out the software side of things. Notice how the master on the left kicks off the conversation by actively pulling that slave select line down to low. Then it writes its data into a buffer to be sent out. Once the transmission is done and verified, the master pulls the slave select line back up to high to cleanly close the session. Meanwhile, the slave on the right, it basically just sits there, chilling, waiting for that select line to drop before it even starts listening.
Okay, let's wire the master to the slave. In our simulation here, U1 is acting as the master, processing button inputs. And look, it's using those exact SPI pins on port C we talked about earlier, pins 18, 23, and 24. It uses them to instantly send commands over to U2 on the right. U2 is our slave, taking those digital commands and translating them to literally change the physical number you see on that red 7-segment display. We have officially made 2 separate brains work as one cohesive unit. How cool is that? There's a quote from our source material that I think just perfectly hits the nail on the head. It says, SPI ensures the reliability of transmitted data, and the master can control the communication process at will. That right there summarizes why SPI is an absolute cornerstone of embedded systems. It guarantees fast, rock-solid control between your main processor and its peripherals. When you press a button, you need to know that display is going to change instantly, every single time, and SPI delivers exactly that. By starting all the way down at the chip level, decoding those pins and applying the SPI protocol, you've just unlocked a massive new capability in your electronics design toolkit. Now that you have the builder's blueprint for making microcontrollers talk seamlessly to one another, the only limit is really your imagination. So what complex system are you going to build next?
Vì vậy không, tức là đầu tiên là phải đặt xuống cái bàn làm sao á, không phải tìm được, phải là phải đặt dây đúng. Cái này thì không biết là cái gì đi chậm. Vãi, giống mấy đếm giờ kỷ lục thế giới Rubik à. Cái gì? Wow. Cái cháy vậy đó. Cái cháy. Có một vậy đó. Ta từng cái sơn mà. Wow. Rồi. Nhanh thôi. Lần này xong. Ông chửi mà ông căng nó mà. Sao dám ông cho vậy? Dám ông cho vậy. Ông căng cái vụ bệnh tay. Chạy được đi. Serial Cong 5. Má sao giờ nghe mấy cái câu chửi như là các em làm như này em ra đồ án được rớt. Quay màn hình lại luôn nha. Hồi sáng thầy Hạnh chửi rớt xong rồi qua Facebook bảo các em làm này rớt. Được. Quay màn hình lại. Phải cầm bộ chứ. Quay màn hình đúng không? Hay là chụp màn hình? Quay màn hình. Sau đó là đưa cho Khoa rồi Khoa sẽ tự biết cách để Khoa dưới. Rồi chơi đi. Được ra cô chú thì bài của tao cũng có mấy cái chỗ sai mà để nào vẽ xong cái hệ chuyển động thì tao sao bài. Hồi sáng cũng chửi thằng Nhân kia mà có chóc không? Nhân nào? Thằng Nhân gì đó mà nó vẽ nó sao vậy? Nói chung là kiểu mày để mày sắp xếp cái u lông vòng đâu? U lông vòng mày không biết. Dạ như vòng vậy. Quay lại một lần nữa, quay lại một lần trong tròn đó. Lấy đâu ra? Nhưng mà em làm em nó nhóc. Rồi. Anh này giàu. Phải biết chỗ nào không cho anh